Continue here through section 5.2. So kind of the setup here where we're at is we're looking at differential equations that look like this. A2y double prime plus A1y prime plus A naught y equals 0. So if you encounter one of these things, how do we classify it? Well, it's a second order constant coefficient homogeneous differential equation. Okay? And last time we said, okay, if we're trying to find a function that makes this work, essentially we're looking for a function whose derivatives are essentially multiples of the original function, because we're getting a linear combination of the function its derivatives equaling 0. And so we make the assumption, or the ansatz, that y equals e to the mx. And if we plug that into the differential equation, we get a quadratic equation, a2m squared plus a1m plus a naught equals 0. And so we have to start looking at what sorts of situations can arise when solving quadratic equations. So yesterday we talked about two cases. So the first case we talked about is if we get two distinct m's. If we get m1, m2, and these are distinct real numbers. Distinct is just a fancy way of saying that they're not the same. Then the general solution is c1 e to the m1x plus c2 e to the m2x. And we showed yesterday that if m1 and m2 are different, e to the m1x and e to the m2x are linearly independent via the Vronsky. Another case we talked about yesterday, if we just get m1, and so if we get a repeated real number solution, in other words, it's got multiplicity 2, then we actually previewed a technique we'll be looking at the week before spring break called reduction of order. We use reduction of order so in this case we get the c1 e to the m1x, and then we make the assumption that the second linearly independent solution is just going to have a variable coefficient instead of a constant coefficient, and it turns out the variable is just x. You just have to slap an x on, and so e to the m1x and x e to the m1x, once again we verified via the Vronsky, those are linearly independent, and so that gets us our general solution. So we've covered the case when that quadratic gives us distinct real numbers, repeated real numbers. So now today we're going to talk about what happens if we get non-real numbers. Okay? All right, so in order to tackle this, we need Euler's formula. And I have 5 Euler's formula t-shirts. That's sort of my uniform for work. I uploaded a video. Typically I go through, there's a couple different derivations of Euler's formula. There's one that involves power series. So I did upload that to the Blackboard site. It's the very first math video I ever made back in 2008. So I did a lot of research and figured out how I could try to make all this happen to make these videos. So it's up there, Euler's formula, the derivation of it, using power series. So it's everyone's favorite power series. Basically, Euler's formula says that e to the ix is equal to cosine of x plus I times the sine of x. So basically, these complex exponentials, or the imaginary exponentials, are just linear combinations of cosine and sine. E to the minus ix then would be cosine of x minus I sine of x if you go through the algebra. And so what ends up happening is that you can add and subtract, and you can show that sine and cosine are actually linear combinations of these imaginary exponentials. So for example, cosine of x ends up being e to the ix plus e to the minus ix all over 2, which you can kind of get by adding these equations together. And you can compare that with our friend hyperbolic cosine, which is e to the x plus e to the minus x over 2. Right? So a lot of the behavior of cosh and cosine is very similar when it comes to taking derivatives because they're essentially the same type of linear combination. It's just real exponentials versus imaginary exponentials. And similarly with sine. And once again, I uploaded that video. If you haven't seen it, it's worth a watch if you haven't seen where this comes from. That's your sine, and then of course the hyperbolic sine, which you're working on the take-home. You got that working for you there. Is very similar to that. Okay. The point is that just like with cosh and sinh being linear combinations of real exponentials, and real exponentials being linear combinations of cosh and sinh, the same kind of argument can be made with sines and cosines and complex exponentials. All right? So for example, if you're looking at y double prime plus 4y equals 0, and you go through the usual assumption there, the auxiliary equation or ancillary equation you get is m squared plus 4 equals 0, which would lead you to m squared is minus 4. And this is where the imaginary numbers come in, right? The negative under the square root flies out, hit you in the eye. What's the, how does this simplify? We got plus or minus square root negative 4. That's plus or minus what? Yep, 2i. Okay. And so if we just plug stuff in what we did yesterday, we could say, okay, well, it's, c1 e to the minus 2ix plus c2 e to the 2ix. But now we've introduced non-real numbers into our solutions, and we want to keep everything as real number solutions. Okay. This is where we're going to use Euler's formula. So Euler's formula says that these complex exponentials are linear combinations of sines and cosines. All right. And so if I go back to my Euler's formula here, if I had some real number in there, let's say we had a b in there, then I could associate this. I could rewrite this as I times bx, and then the b would come into here. So the coefficient b ends up being the frequency of the sine and cosine. So instead of writing our solution this way, we're going to write it as a c1 sine of 2x plus c2 cosine 2x. So once again, the frequency here, 2, comes from the coefficient of the I, right? And more generally, and this is something that I think was on your first test or take home, I forget which one, if you're looking at y double prime plus omega squared y equals 0, for some positive number omega, the equation would be m squared omega squared is 0. So m squared would be minus omega squared. Once again, taking square roots. The negative flies out, hits you in the eye. Omega is assumed to be positive, so that's plus or minus I omega. That omega is then going to be the resulting frequency of the solution. So it's a C1 sine omega x plus a C2 cosine omega x. So that's the same frequency there. Okay. I'm pretty sure if you could look back, this was either test 1 or take home 1, where I gave you this and had you verify that. Just like in yesterday when we did the one with the hyperbolics. It was something that I had sort of given you back the first week of class. Okay. Any questions on what's happening here? So this is how we handle the imaginary roots. Comes from Euler's formula. So just to kind of couple it with what we did yesterday, y double prime minus k squared y equals 0 gives us sinh and cosh. Y double prime plus omega squared y is 0. That gives us sine and cosine. Okay. Then depending on the application, you'll see these. So these are a couple classic scenarios. We're going to see a lot of mileage out of this type of equation here. This model's harmonic motion. So we'll see that come up again. You see the connection, the similarities, folks? Have you seen Euler's formula before? Has that been something you've run across in your adventures? Did you ever see the Euler's formula before? No? Did the feed die? Did the internet die? It says the meeting's still up. Saw it but not really in the class. Yeah, that's typical. I always make time for it because it's like kind of a big thing. Anyway, the video's up there. It's like I said, it's 2008. So I'm going to sound a lot younger. Because that was quite a few years ago, 2008. How many years ago was that? Well, anyway. Okay. So there's that. Okay, let's take a look at this one. So y double prime plus 2y prime plus 4y is 0. Once again, we've got a second order constant coefficient homogeneous differential equation. So we're going to assume y equals e to the mx. We get our m squared plus 2m plus 4 is 0. And now we'll try to solve that. The first question is, does it look like it factors nice? Well, we could try. If it doesn't look like it factors nicely, we'd have to hit it with the quadratic formula. So we'll go ahead and calculate the discriminant there. The b squared minus the 4ac we get a negative 12. And that tips you off right there. You're going to get non-real solutions. Okay? So that means that we're going to have oscillations. So when you get your quadratic is going to have non-real zeros, that means you're going to have some oscillations. So m would be Quadratic formula, opposite of b, plus or minus the square root of the discriminant, all over 2a. And once again, let's go through the algebra to correctly simplify this, because I've been teaching this class for years. And even though this is differential equations, this is the capstone, this is the culmination, essentially, of years of algebra, trigonometry, and calculus, there are often many mistakes that get made just simplifying this, which is going to completely mess up your solution. You can't just cancel the 2's. You have to do other things. So let's just go through the algebra. It doesn't take that long to do. First off, we need to correctly simplify the square root. So we need to break it down into factors. Here, let's just break it down. Let's do the -1. 4 and 2. Okay, now let's just go one at a time. The negative under the square root flies out, hits you in the eye. The square root is really a power, so it works well with multiplication. -2 plus or minus. The square root of 4 is 2, so that's 2i root 2 over 2. And now we can either factor the 2 out and then cancel the common factor, or we can split the numerator, however you want to do it. This is the correct way to simplify our answer. Oh yeah, thank you. 4 times 3. Thank you. Yep. This is the 3. Thank you. It helps if you factor things correctly. There we go. Okay. So the most common mistake I see doing this is people canceling off these 2's and just like forgetting there's a real number out front. And I'll show you why that's a big deal here in a minute. But you know, if don't, in other words, don't neglect this term. It's a -1 plus or minus I root 3. So now we have to figure out, how do we handle that? What kind of solution does that come up with? Because this -1 is a pretty big deal. Okay. So you want to make sure that you split things up and then cancel, or factor and cancel. This -2 just doesn't disappear. Okay. All right, here's how we handle that. We go back and we say, okay, well, what if I had an e to the a plus ibx? All right. So how does the exponential work on this? Well, you could multiply the x through to get e to the ax plus ibx. And then it turns out the same properties of exponentials that we've been using carry over here to these imaginary exponentials, these non-real exponentials. So I could write this as e to the ax times e to the ibx. This is a real exponential, so that'll just stay out front. This is the complex exponential we can hit with Euler's formula. Yeah, right. So then we could write this as sine of bx, or excuse me, cosine of bx plus I sine of bx. Okay. And once again, as you know, you put in your linear combinations. So you're going to have this real exponential multiplying your oscillation. All right. So with your m like this, your solution is going to be, this is like your a, so that's what's going to be in the real exponential. So it'll be e to the minus 1x times, and then you got your c1, and then your oscillation. Sine of, and that's the frequency of the oscillations. We'll write this as x square root 3 plus c2 cosine x square root 3. Okay, so that's how we would write that. And this is an important type of phenomenon we're going to see, because these are damped oscillations. All right. So this is why I wanted to have Desmos up, because I want to show you once again how you can check these answers using Desmos. Let's fire this up. So we're going to have y equals, and you can just even type in c1, or excuse me, e to the minus x, we need that up there, times, and you can just type in c1 sine of x square root 3. So you just type that on in. Whoops. Gets a little persnickety there. Plus c2 cosine x square root 3. And we'll put sliders in, kind of see what's going on here. So we can adjust these sliders. These are all the different things. Okay. Now, if we call that f of x, then we can check our differential equation. Differential equation says y double prime plus 2y prime plus 4y should be 0. So f double prime of x plus 2f prime of x plus 4f of x should be 0. And sure enough, y equals 0, aka the x-axis. So that shows us what's going on there. Okay. But I want to look a little bit more at this behavior here. Go like 0 to 10. And y-axis, negative 0.25. 0.25. Okay, so what's actually happening here with these with this type of function? So you might recall back to like your pre-calculus or trigonometry class. If you're graphing something like y equals, a sine omega x, or y equals a cosine omega x. This coefficient here, that omega, is your angular frequency. Right? So if omega is 2, that means that the sine and cosine wave is going twice as fast as normal. Right? The period is going to be the regular 2 pi divided by omega. That's why it's called frequency. How frequent it is compared to the standard. Okay. Do you remember what A stood for? What did A stand for? Yeah, amplitude. And that kind of gave sort of the maximum displacement from the baseline. All right. So normally sine and cosine run between -1 and 1. So the displacement here would go from minus a to a. So minus a would be like less than or equal to, say, sine less than or equal to a. All right. So this kind of thing was exploited all over the place in calculus when you had squeeze theorem calculations. But for us, this a is a function of x. So we have e to the minus x. And so what that says is that these waves are trapped between e to the minus x e to the minus x, or being multiplied rather, and each of these things are going to decay the wave to 0. Right? Now we'll talk about how we can figure out exactly what that number is here in a minute. But let's just zero out C1, and then we'll put that as C2. But you can see then that the oscillation is damped by these exponentials, and so it attenuates on down. Okay, so damped oscillations, that's a big deal. That's why you want to, take the time to simplify this correctly, and don't forget about this. It happens so many times. And if you do leave it off, then you greatly simplify what's happening, and it could cause issues later on with what you're doing. It can completely derail the problem. All right. Okay. So here's the summary of what we've been working on the past 2 days. Right. So if you start off with the e to the mx, you get two distinct real numbers. There you go. Got a repeated real number. There you go. If you got pure imaginaries, you got your oscillation. If you've got things that are non-real but not pure imaginaries, then you get your exponential times your oscillation. Okay. So I don't know if people make note cards anymore. That would be a note card for me if I were in the class. But once again, the best way to remember this is just to do all the practice. Okay. All right. Since we've moved into these non-real roots and we're getting oscillations, there are alternative ways to write solutions if you've got sines and cosines of the same frequency. So we've got this little thing from trigonometry here. So you may recall sum and difference formula. So if you've got sine of alpha plus beta, that's your sine of alpha cosine of beta plus cosine of alpha sine of beta. So if you're looking at sine of, say, omega x plus some angle phi, you could write this as sine omega x cosine phi plus cosine omega x sine phi. And so this is like some constant C1 and some constant C2. All right. So instead of looking at a linear combination of sine and cosine of the same frequency, you can rewrite it as a sinusoid with the same frequency, but we've got a different phase shift. So this is called the phase angle, or the phase phi. Right. So what you can do is you can go through and figure out what these are in terms of the coefficients here, a and b. Just use a little Pythagorean identity. So let's see. So let's say you have, I'll want to be consistent here. Let's say you've got a sine omega x plus b cosine omega x. And you want to set this equal to a, capital A sine omega x plus phi. So what you can do to figure out how all these things relate is you can start with your a sine omega x plus phi, and you can use your sum and difference formula. The cat's very excited today. So using the sum and difference formula, and she's all over the place here. So you notice that cosine of phi is what's multiplying the sine omega x. So I would have A cosine phi sine omega x plus the sine phi is what's multiplying that cosine omega x. A sine phi cosine omega x and so this is little a and this is little b, and so we get a system of equations here. We got a cosine of phi is little a sine of phi is little b, and now I can exploit the Pythagorean identity. If I take a cosine phi squared plus a sine of phi squared, then on the one hand, that's going to be a squared cosine squared phi plus a squared sine squared phi, and I can factor out that a squared. And cosine squared of phi plus sine squared of phi, regardless of what phi is, that's always going to be what? Yep, that's always 1. So that's going to be a squared. But on the other hand, a cosine squared is little a sine phi is little b. So a cosine phi squared plus a sine phi squared, that's also going to be little a squared plus little b squared. So the net amplitude here, when you add this sine wave with amplitude little a and this cosine wave with amplitude little b, the net amplitude is going to be the square root of a squared plus b squared. So this gives us capital A squared plus b squared. And if we assume, just keep a positive amplitude, there's that. And so now I go back to my system here. I know what capital A is, so I know that cosine of phi, a cosine of phi is little a. So that means cosine of phi is little a over big A. That's little a over the square root, a squared plus b squared. Capital A sine of phi is little b. So sine of phi is little b over a. That's b over the square root a squared plus b squared. Okay. So that's where these formulas come from. They just don't come out of the air. But it tells you how you can rewrite the sum of sine and cosine if they have the same frequency. Write them as a single sine wave. Okay, so that's the key. You need the same omega. You need the same frequency here. And then you can rewrite it as a single sinusoid with the phase. All right, so if we go back and look at this solution we had earlier, we got that. Let's take a look at this one here. So we got y equals e to the minus x oh, actually, let's go through a specific example to see that. So we should be able to do this here. So here's our exponentials, whatever. So we should be able to put on here square root c1 squared plus c2 squared. And there we go. And now you can see how, so I'll make these all the same. Same color here. And you can now see how that this curve, right, is trapped between these two exponentials. So you can actually see the squeeze theorem happening there, right? It's sort of trapped between these two exponentials, okay? All right. So sometimes, depending on the situation, you're going to want to rewrite your answer. If your answer is given this way, you're going to want to write it that way. Notice you got two arbitrary constants here, right? You've got the amplitude and then you've got the phase. Okay, so you start with two arbitrary constants, you end up with two arbitrary constants. Some scenarios, instead of writing it as a sine wave, you want to write it as a cosine wave. So there's slightly different formulas if you want to write it as a cosine instead of a sine. Or you could always write it as a sine and then just use the cofunction identity to get it in terms of a cosine. But it just all depends on what you're doing, right? I've seen different applications want different things. So let's finish off today looking at this example. Solve y double prime plus 4y is 0. Y at 0 is negative 3. Y prime at 0 is 8. Once again, we identify this is a initial value problem because they're giving us a point when x is 0 and they're giving us the slope at the same x equals 0. So we know from before what we started off with, the first example I think we did today, we know that we get this. Right? So so we had that from before. That's the general solution. We can now impose the initial conditions. Y at 0 is negative 3. So when you plug 0 in for y, what's going to remain here? When you plug in x equals 0, what do you get for y? Yeah, C2. So C2 you get minus 3 right off the bat. And now we look at y prime. So we take the derivative here. Remember, when you take the derivative of the sine and the cosine, what's going to pop out from the chain rule? Yeah, factor of 2, good. So we'd have 2 c1 cosine 2x minus 2 c2 sine of 2x. And once again, common mistake forgetting about that 2. All right, so don't forget about that 2. Y prime at 0 then. We're going to get 2c1 cosine of 0 minus 2c2 sine of 0. So y prime at 0 is going to just be what? Two C1. And that's supposed to be 8. So C1 is going to be 4. And so one way to write our solution, y is C1, do we do sine? Yeah, C1 sine of 2x plus C2 cosine of 2x. One way to write that answer would be 4 sine of 2x minus 3 cosine of 2x. Okay, so we'll fire up Desmos. Number one, we'll check it, and then we'll write it into the other form, and then we'll talk about another way you can go about solving it if you know ahead of time you want the other form. All right, so let's go ahead and fire up Desmos here. So take that out, and we'll take this out, take that out, take that out. Okay, so we got f of x equals 4 sine of 2x minus 3 cosine 2x. Let's do something reasonable here. Let's go like 0 to 10 or something. And negative 10 to 10. Okay, there it is, a little sine wave there. Let's check the initial conditions. F of 0, supposed to be negative 3, it is. F prime of 0, supposed to be 8, there it is. And looking at the diffie q, y double prime plus 4y should be 0. So f double prime of x plus 4f of x should just give us the x-axis, boom, y equals 0. All right, so once again, that's how you check graphically these initial conditions. F of 0 is negative 3. That gives us the point on the graph, 0, negative 3. Once again, what's the derivative tell us? That should be the what? That should be the slope at 0. So if you zoomed in, you should see a slope of 8, which I'm not going to do. All right. All right, so suppose you solve it that way. And they say, okay, well, that's great, but I really wanted it to look like this. All right? I really wanted it to look like a sine omega x plus phi. All right? So we can take this and convert it to this using these formulas here. All right? So first off, omega is going to be the same omega as before. So once again, for this to work, you need the same frequency. So the omega here is going to be 2. So omega is going to be 2. A, think of Pythagorean theorem, that's just going to be the square root of little a squared plus little b squared. So what's our net amplitude going to be here? Yeah, 5. Okay. And then we look at the angle, figure out what the phase angle is. Cosine of phi is going to be a over that squared. So it's the coefficient, what was attached to the sine. So that's going to be 4/5. The sine of phi, you look at what was attached to the cosine, and then divide by the new amplitude. So that it's a, right? To figure out what the cosine is, you look at the coefficient of sine, divide that by the new amplitude. To figure out what the sine is, you take the coefficient attached to the cosine, divide by the amplitude. And that's just a consequence of the cadence of that identity we use to get these. All right? Now, are these friendly numbers? Like, do you recognize this off the unit circle? Is that like a pi over 4 or a pi over 3? The answer is no. There's no root 2's in there. There's no root 3's in there. We have no idea what these are. So I have to use the inverse trig functions. So the question is, which inverse trig function is going to help me figure out what phi is? Well, I can tell since I have both cosine and sine. If cosine is positive, but sine is negative, what quadrant am I going to be in the unit circle? If cosine is positive but sine is negative, what quadrant am I in? So remember, cosine is x, sine is y. So if cosine is positive, sine is negative, that's going to put me here. Now if I take the inverse cosine is always going to land me up here because that's a positive number. If I take inverse sine of a negative will land me down here. So we could do phi then is the inverse sine of negative 3/5, which because of how inverse sine is, I can move that out front. And so I could write my answer this way as 5 times the sine of 2x minus the inverse sine of 3/5. So that would give us our phase angle phi. And once again, we can check this graphically. We can see how this matches up with what we had before. So y equals 5 sine of 2x minus the inverse sine, I'm going to write it as arc sine in Desmos because I don't trust it, of 3/5. We'll make it a different color. So there's the solution as we had it. There it is. Okay. Now, if you knew from the start that this is what they wanted, let's say that's the only thing they wanted, then what you could do is you could plug this into the diffeq. You follow? You could actually say, okay, well, if you want this, we know that the omega is going to be 2. We get that from the diffeq. So then you could say, okay, well, my y is going to be c1 sine 2x plus c2. And then you can impose the initial conditions here. Right? Y at 0 is negative 3. So you plug 0 in. So y at 0 is negative 3. You plug 0 in, you're going to get c1 sine of c2 is negative 3. And you can plug 0 in here. 2c1 cosine of c2 is going to be 8. And you're going to get a system of equations very similar to the ones that we had that gave us these formulas. All right. So it's up to you how you want to do it. You can just solve it the one way and then convert it, or you could just from the get-go do this method, but then this will take you through the trig identities we had before. Okay. All right, and then there's your homework to work on, which hopefully you're doing at least some practice with this. All right, so there's that. So tomorrow then we're actually going to be in the situation where we're going to actually start looking at non-homogeneous equations. So instead of having 0 here, we're going to have an f of x. And so it takes a few sections to get through to solving a non-homogeneous piece. We're going to prove a little thing about non-homogeneous equations. And then we're going to look at, well, what if the f of x is built up of functions that we know about? And then eventually we'll move into what happens if the f of x is things we don't know about. So we'll be looking at method of undetermined coefficients, method of variation of parameters, and then finally reduction of order. All right. That'll take us through the rest of the first part of the semester, and then we'll have our spring break, and then we'll come back and start looking at applications and generalizations. Okay? So I appreciate you tuning in, folks. Have a great rest of your day. It's supposed to get warmer. Enjoy the sunshine, and we'll see you back here tomorrow.